So let's zoom in further into the wave function, the dream that stuff is made of. What is the wave function? Is it a physical entity, a wave, or some kind of a mathematical construct? And then you also brought a measurement. What is the measurement problem?
Okay. Well, first of all, this wave function is really, has gained a lot of significance, partly due to Schrodinger, because he is the one who sort of cast quantum theory in that form. But I should say that it was actually Heisenberg who, my understanding is Heisenberg was actually the first to get that, to get to the mathematical structure of that underlies the theory. And his form of the theory was called matrix mechanics. And it has to do with a kind of a mathematical form that deals with matrices, which are basically arrays of numbers. And this was a bit esoteric. And in fact, when Heisenberg obtained this, he didn't even actually know what matrices were. He was just working with, how do I get this data to kind of give me something that seems to be empirically valid? And Schrodinger didn't like that. So he wanted something that seemed more physical. So he did something with Heisenberg's matrix mechanics that kind of dealt with a very special case of it in terms of positions. So when you look at this matrix mechanics and you say, I'm going to prefer to know like where my system might be located, then you're dealing with positions. And that's what Schrodinger did. And when he did that, what happened is you have to project the quantum states. This sounds a little esoteric, but just let it wash over you if it doesn't make any sense. You have to do a mathematical procedure in which you take a quantum state and you project it into what's called the position basis. So you kind of take this quantum state and say, what is its relation to all the possible positions my system could be located? And when you do that, you get what's called the wave function. But it's a kind of a construct. It's technically called a probability amplitude. So to be completely accurate, you can get a probability amplitude for any kind of what's called observable, something you might want to measure. You can get a probability amplitude for the momentum of a system, or the energy of a system, or the kind of spin that a system is engaging in. So these so-called waves are actually probability amplitudes. And that's why you have to square them to get a probability. They kind of underlie the probabilities. So they have wave-like properties. And I do think, in terms of like, are these waves real? Well, they're not like water waves. They have important mathematical differences from things like classical water waves and sound waves and things like that. So they are not classical in that sense. But I take them as real in the sense that they are referring to something in the world. So in other words, I guess I have kind of a middle way. Like I wouldn't say, I wouldn't say, oh, the wave function is this, magical wave of consciousness. And it's like, no, I don't. I think that's starting to get a little bit too whimsical and not philosophically responsible, because technically at the relativistic level, wave functions don't exist, not for position. So it's an idealized notion that has physical content, but it does not have the kind of content that it's not like a water wave, and it's not something we want to kind of identify with nature at all levels, because again, it doesn't necessarily apply to nature at all levels, depending on what observable you're dealing with. But what I suggest is that it is revealing the structure of a domain of possibility that is real, that is really there. In other words, this is referring to something in nature. So whether or not this is observable, and no, it is not directly observable, but these probability amplitudes are, I argue, they're physically efficacious because they really are describing something about nature.